In the last lecture, I explained to you about SR flip-flop. In that one, when the inputs of set input pin and reset input pin are equal to 1, there is an undesirable condition of the indeterminate state in the SR flip-flop. This indeterminate state can be eliminated by using the D flip-flop. In this lecture, I will explain you about D flip-flop. This is the logic diagram of the D flip-flop. This logic diagram of D flip-flop is just similar to SR flip-flop, and in this logic diagram we are adding one more NAND gate and given a number 5. Here it consists of the inputs are D input and clock pulse. Here the outputs are Q and Q complementary. Now when we are applying clock pulse equal to 1, whatever the input D we are applying to this logic diagram, the output we are going to find out. So when clock pulse equal to 1, here we are going to apply 1 here, here we are going to apply 1 here, and this is the characteristic table of this corresponding D flip-flop. This is the present state Q of T before the clock pulse. This is the D input. Q of T plus 1 is the next state after giving the clock pulse. So here when we are considering present state equal to 0, D input equal to 0 means here we are applying D input equal to 1 here, D input equal to 0 here. So by applying 0 for the fifth NAND gate, we are going to find the complementary of 0 equal to 1. Here we may get 0, 0 and 1 for this third NAND gate. The output of this third NAND gate is going to be 1 here. The fourth NAND gate output is going to be 0 here. So after applying these inputs to the first NAND gate, second NAND gate, here we know the 0 for the second NAND gate means definitely the Q complementary is going to be 1 here. By applying this 1 here, Q is going to be 0 here. By applying 0 as D input to the D flip-flop, the next state Q is going to be 0. Now that one we can write here. I consider the second case. When D input equal to 1, the present state is 0, means we are applying D input value equal to 1 here. By applying D input value 1 here, we are going to get the complementary of 1 equal to 0. So for the fourth NAND gate, output is going to be 1 here. Third NAND gate output is going to be 0 here. By applying 0 as input to the first NAND gate, the output is going to be 1 here. After applying here, the Q complementary is going to be 0. So when we are applying D input equal to 1, the output is going to be 1 here. Considering the third case, present state equal to 1, D input equal to 0, and the fourth case, present state equal to 1, D input equal to 1. By considering from this first case and second case, we may know that when we are applying D value bit, if we apply 0, the next state is going to be 0. If we apply D input equal to 1, the next state is going to be 1. That is independent of the present state. The next state is going to depend on only the value of D input. By this, we may get when the present state equal to 1, D input equal to 0, directly D input is going to be the next state. By applying present state equal to 1, D input equal to 1, the next state is definitely 1. So in this D flip-flop, whatever the inputs we are applying to the D, the next state value is also depends on D input. If it may be 0, next state is 0. If it may be 1, the next state is going to be 1. Now by considering this characteristics table, we may find the characteristic equation for the next state, that is Q of T plus 1. By considering the minterms, so here to find out the equation for the next state, here in the row wise, here I am considering Q of T, column wise I am considering D input. So here for 0th minterm, 0, 0 combination, Q of T plus 1 equal to 0. In 0, 1 combination, 1 minterm, here 1. In 1 0 combination, 0. In 1 1 combination, nothing but third minterm, which is equal to 1. By combining the adjacent ones, we may get a prime implicant here that will be equal to D. So, the Q of T plus 1, the characteristic equation for the next state is going to be D. This completes the explanation of D flip-flop.